Oh, really? You're late.
Of your name.
Great.
Like the company. Great. Good.
Thanks so.
Okay, let's go ahead and get started. I am socially aware enough to know what you want me to do today. You would like me to review for the final, no new material. That ain't gonna happen.
Remember my name.
We got some new stuff to cover. We've got places to go, people to see. But on Tuesday, next week, I will have a review session where I just worked problem after problem after problem, getting us ready for that final exam, which is really just another midterm. It's just going to cover the new material with fluids and rotation. Today, we're going to cover rotational dynamics. Those of you that have worked on cars, the big idea today is torque. And I've titled this, Why is there a heavy end? You've all gone to a moving party where there's some big piece of furniture or a refrigerator or freezer, and you know that there's always one end that you don't want to grab, okay? Elder Uchtdorf gave that very classic talk where he said, lift where you stand, and just wherever you are, do your part and lift. But it turns out that there's some places that are better to stand than others, okay? Near the light end, and we'll talk about that in today's lecture. Would someone be willing to give us an opening prayer before we get started? A prayer of thanks.
Our dear kind Heavenly Father, we bow our heads before thee this day and thank thee so very much for the opportunity we have to be here, that we could all arrive here safely, and pray that we can continue to be safe throughout the remainder of our day. We thank thee for the opportunity we have to learn about physics and how that world works, and that we can approach today with curiosity and joy in learning. And thank thee for our professor, and ask thee to please bless him with safety and health, and do so in the name of Jesus Christ. Amen.
I'm especially thankful that you came back safe. I saw those horrible crashes on Interstate 70. It just so glad that you're back. Before we can get to this idea of torque, we need to cover some basics, and it'll be basic. It'll be something that some of you will find trivial, but we've got to cover them to get where we want to go. And so to begin with, let's go on a field trip out to a snowy field. And in the snowy field, we find ourselves a frictionless pond of ice. Why wouldn't it be frictionless? And we lay a meter stick on that frictionless pond of ice, and we push on it. We push on it with 50 newtons to the right and 50 newtons to the left. Now, I taught you Newton's second law, and that looks like a net force of 0, and so that predicts that there will be 0 acceleration, and that's what you expect. However, here's a wrinkle. If I push there with 50 newtons to the right and there with 50 newtons to the left, I still have a net force of 0. When we were doing linear dynamics, we always drew our free body diagrams as a dot, and we put the forces on that dot. And we didn't care where the forces were applied, just how many are to the right and how many are to the left. So that's still net force zero, which predicts zero acceleration. And your gut tells you that that isn't what's going to happen. Your gut tells you that that thing is going to rotate. Okay. Now, if you think carefully about that, what that means is Greg lied to you. Okay. And that's because you weren't ready for the truth. Okay. And now you are. Okay. There is one point on that meter stick that obeys Newton's second law. Which point is it? Yeah. Which point is not accelerating? That center point there is not accelerating. And so what we find is that when things are extended big enough that they can rotate, Newton's second law only applies to one point, and that's the center of mass. And we're going to talk about finding that center of mass in just a moment. But essentially, Newton's second law, I taught you a lie. I taught you that. And what I was hiding was this. Now, you remember when we were back in that second part of the class before the second exam, we were dealing with cannonballs and baseballs and things that were compact, where we didn't worry about any flopping or rotation at all. And so that's why we could represent those things as a free body diagram of a dot. And that dot represented the center of mass. Now, I've got Britton, would you help me out here? I've got an odd-shaped object, and I've got if you could stand over there, I'm going to have you catch some things. I've got a flashlight in there right at the center of mass, and if you only concentrate on the flashlight, only look to the light, ignore everything else. What you'll see is that light will travel in a nice parabolic curve predicted by Newton's second law. Okay, send it on back. Okay, now I also, whoops. Aha. Not yet. I have here a system that has two tennis balls, and symmetry suggests that the center of mass is going to be right here where the orange ball is. And so if you only concentrate on that orange ball, it should follow that nice, smooth, parabolic path. A little higher this time. Perfect. Now, if I were to put that somewhere, oops. Oh, can't do it. Okay. Won't slide. But this one will. I've got another system, and this one has is that a heavy ball there? Yes, very heavy. And this one's just a light tennis ball. Your gut tells you that this point in the center is not the center of mass. That's not the average location of the mass. And so now, if you concentrate on that orange ball, what you're going to see is something that flops all around, okay? Oh, you almost owned the whole university. You could have sued us for everything. So, your gut's telling you that the center of mass is closer to this heavy one. And actually, we've rigged this system so that the center of mass is right about there. And so now if you concentrate on that orange ball and ignore everything else, oh, this is harder than I thought. Okay. Did it go in a nice smooth path? Tell me it did. Just thank you. Thank you, Britton. He's great. Okay. This picture is of my redheaded son, the orthodontist that makes more in a year than I'll make in a lifetime. The picture was taken by my son-in-law, and if we could somehow identify his center of mass, if we could make that center of mass for Christian glow, we would see that it would travel in a nice parabolic arc. Now, I wanted to put that picture on the cover of my textbook. Okay, not the textbook you're using, but the textbook for the Physics for Poets class. And on the 8th edition, I wanted to put that picture and send it to the publisher. Well, the publisher called me and he said, Greg, we can't use that picture. I said, well, why not? That is one funny looking kid. That funny looking kid is my son. There's a long pause and then he said, yeah, but he's still a funny looking kid. And so instead they used this not so funny looking kid to convey the same idea there. Okay. Now, how do we find a center of mass? Well, you've done it semester after semester after semester. The fact that you're at BYU tells me that you were all A students in high school. And so you were, you know, the type of students that ran to calculate your GPA every semester. And this is the way you do it. Okay. I hacked into the Canadian higher ed system and got my best friend's transcript. Jeff Adams, a co-author of your text. And you see that he's really good at physics, but not so good at chemistry or calculus or music or psychology. If we wanted to find the average grade, he's got an A, he's got some C's. I guess his average be somewhere halfway between, right? About a 3.0. Yeah, that doesn't feel right. So what you would have to do is do a weighted average. Okay, a weighted average. I would take each class grade, there's the A in physics, and that happens to be a 4-credit class. This is the C in calculus, and that's a 3-credit class. This is the C in chemistry, and that's a 4th-credit class. And when I add those all up, I get a GPA of 42, which seems high, but it's Canada, so it's inflated. Okay. Well, we've got to divide by the weighting factors, by the total number of credits. And so when I divide by the 17 credits, I get a GPA of 2.5. And that's how you find a center of mass. Now, that's not Jeff's GPA. He's one of the smartest individuals I've ever met. And I feel bad telling this story on him. So I'll tell one on myself. When I went to MIT, I suddenly found that every nation on earth had sent their geekiest humans to MIT. And when I got there, I found that I was always at the end of the class. In grad classes, everyone either gets an A or a B. The top students get an A and the bottom students get a B. And I was getting a B in every class. I was not just in the bottom half, I was the bottom half, okay? And so my father called at the end of the semester, first semester, and he said, how did it go, Greg? He was so excited that his son had gone to MIT. He was telling everybody. And I said, I got a 4.0, Dad. Oh, that's so wonderful, Greg. I knew you could do it. I forgot to tell my dad that MIT is on a 5-point scale. Yeah. It's a sin of omission. So the second semester, I figured things out. I got my feet underneath me and I got an A in all of my classes. So my dad calls again. How did it go, Greg? I said, I got straight A's, just like last time. And I didn't say a word. Okay. And I never told him. I mean, he passed away a couple of years ago and he knows now. And I'm going to have to face him, but you know, he never found out while he was alive. Okay. Now, let's look at physical systems. If I have something that's made of uniform material like oak, like this beam here, the center of mass is just where you think it would be, in the center. As simple as that. And if I wanted to put a number to that, I would set up a coordinate system where this is the origin, and I would say the center of mass is at 2 meters right there. Well, it gets interesting when you add something else. If I add this 25 kilogram block, at 3 meters. Well, now I have to move that center of mass for the system. And is it going to go left or right? Well, your gut tells you it's going to the right, but how far? Well, I do a weighted average. I take the center of mass for the beam and I weight that by how important the beam is to the whole system. It represents 50 kilograms of the total mass. And then I add the center of mass of the block and I weight that by how important it is to the whole system. It represents 25 kilograms of the total mass. And then I have to divide by the weighting factors the total mass. And that's going to give me an answer of 2.33 meters. And so that tells me that the center of mass moved to the right by 33 centimeters. Check that your neighbor's on the bus, please.
This, yeah. Technically.
Okay. Now, you have some homework problems where you have to find the center of mass for some systems. And in a system that has more than two objects, you would just generalize that. You take the center of mass for the first object times its mass, center of mass for the second object times its mass, and so forth for as many objects as you have, and then divide by all the masses. And in one of the problems, you have to do that in 2 dimensions, in both x and y. And for y, you just replace all the x's with y's. It's no different. Okay? Are there questions on finding the center of mass? Everyone feel like you could do that on an exam? Okay. New topic, stability. Okay. Are we stable? Have any of you been to the Leaning Tower of Pisa? Were they letting tourists go up in the tower when you were there? Okay. I went when I was 8 years old. My family lived in Germany. My dad was in the Air Force. And I looked at that tower and I thought, I don't want to go up there. I was afraid of heights, and that just didn't seem like something I wanted to do. Well, it turns out my dad, bless his heart, was too cheap to take all of his kids up into that tower. So I got away with it. But suppose, if you will, that an entrepreneur came along and said, you know, we could fit more tourists in that tower if we just built it up one more level. Well, that's a problem, okay? Now with a regular high rise, you could build it up and it wouldn't tip over because all you're doing is raising the center of mass. But with the Leaning Tower of Pisa, when I add that extra floor, I'm not only raising the center of mass, but I'm moving it over to your right. And as soon as that center of mass gets beyond the foundation, the support, it goes unstable. It goes unstable. So that's the first big idea about stability. An object is stable when its center of mass is above the foundation. Now, years ago, they had a problem with a Suzuki Samurai. Any of you heard of that car? Yeah, there was a problem with that car, right? It got recalled. It's a wonderful car, great car. Its only problem, its only sin, was that when it went around a corner, it would tip over. And some people didn't like that, you know, it's all preference. The problem was it was tall and it had a narrow wheelbase. And so if you got on a banked curve, you could get that center of mass out beyond the wheels of the car and it would tip over. Now, you can have fun with your friends by challenging them to get their heels right up against the wall and touch their toes. And I'm telling you, doesn't matter how athletic they are not going to be able to do that, okay? And the problem is that as you bend over, you move your center of mass from where it started, right behind your belly button, out forward. And as soon as that center of mass gets beyond your toes, you tip over. Now, if I'm not up against the wall, I can touch my toes, which for a 70-year-old man is, that's not nothing. Not a pity clap. No, no. People, no. Okay. Why can I do that when I'm not next to the wall? The caboose. Caboose. Watch. It goes back, and that keeps my center of mass. What? That keeps my center of mass over my feet and keeps me stable. Okay. So you're a rough crowd. Okay. Now, this car went into the drink probably around 2 a.m. when the bars closed, and they're trying to get it out of the water. And as they lift it up, the center of mass for the system went beyond that support right there, and it went right over. Yeah, yeah. So they brought in a bigger crane to get out the smaller crane, and I bet you know where this is going.
No.
Yeah. Okay. Yeah. Okay. Fun times. Is anyone here engaged to be married? Raise your hand. Okay. Quite a few of us. Whoa. Have you met the in-laws? Yes. Okay. That go well?
Yeah.
Okay. Now, if you want to impress the in-laws next time you're there, what I suggest you do is at dinner, take your fork and your spoon and ram them together so that they'll never quite be the same. And then take the toothpick you were picking your teeth with and use that to balance. See if I can do this. Balance it on your glass. And then if you really want to impress your future mother-in-law, just light the ends. I'm not sure how this is going to go. Sometimes it works, sometimes it doesn't. Oh. Yeah, that mother-in-law is going to be very impressed. Could you see that in the back? Yeah, not so much. Well, you chose those seats, my friend. Okay. But let's see if we can make it more visual. Green Acres is the place for me. Oh, life for me. Okay.
Oh.
There's a chance this will go very bad. Yeah. Okay. Now, I would argue that the center of mass is not above the support. The support for this system is right there at the top of the pole, but all of the mass is down here. And so that principle that we had up there, that something is stable when the center of mass is above the support, that can't be the whole story. That can't be the whole story. So what else do we have? Otherwise, it seeks a point where the center of mass is directly below the support. What that means is I know the center of mass is somewhere below this point right here where the pole meets the board. And so it's got to be somewhere along this pole. I'm not sure where, but somewhere along that pole will be the center of mass. Now, in about 20 minutes, we'll understand why that center of mass seeks that location underneath the support, and we'll use the idea of torque to understand it. But for now, that's just a principle that defines stability. Now, I can use this idea to find the center of mass for a complicated object. This is kind of a complicated object. And if I hang this object from some point, I know that the center of mass for this thing is somewhere below that support right there. So it's going to be somewhere directly below. Oh, can't draw a straight line. Okay. And then if I hang it from a different point, it's got to be somewhere directly below that. And then if I just want to check that my answer makes sense, I would hang it from a third point, and it would be somewhere directly below. That's the best I can do, people. That is miserable. Anyway. One more demo here. My friend Bobo and I have been practicing this and preparing for this for a long time. Bobo, my friend, can ride a tricycle, a unicycle actually, even more impressive, on this high wire. Bobo, are you ready? Oh, no, no. Oh, I'm sorry, Bobo. I'm going to get you. That was my fault. Okay. That was your fault. Okay. That was bound to happen. Okay, let's try that again. Come on, Bobo. Do your best. Oh. Come on back. Come on back. Yeah. Okay. Okay. Now, clearly, what's going on here is the principle we just talked about. The key is these lead balls down here at the end of these poles. Those have a high density and hence a large mass. And so that means that the center of mass, the average location of the mass, is going to be down here somewhere. And symmetry suggests it's going to be halfway between these two lead balls. And so somewhere like here. And so if Bobo tips, this principle says that that center of mass is going to seek a location, for reasons we'll understand in a few minutes, seek a location directly below the support, which is where the high wire meets the wheel, right here. And so if he tips, it's going to right itself automatically. Now, have any of you had the opportunity to visit the Science Center in Seattle? Yeah? Okay. They have this, oh, that's if it didn't work. Sorry. They have this display there where they've taken a Schwinn bike and they've taken off the rubber wheels so that it can ride along this metal track high up in the sky. That's my wonderful wife, Sandra. And you see that she's really not very worried about this. She's very comfortable with that. And she's stable because attached to the bike is this long bar, and at the end of the bar is a very large mass. And that means that whenever the bike tips, that very large mass, which represents most of the mass of the system, is going to seek a location directly under the support, which is right where the wheels attach to the track. And so it's going to self-right itself. And you see that she is just not She's not at all worried. She should be, but she isn't. I, on the other hand, am scared spitless. Okay, I am just terrified. The first time I went on this, it was brand new. And I went to the science center with my young children, and they just guilted me into getting in line. They couldn't go on it. They were too young, but they said, you got to go on it, Dad. And so I waited in this line. And when I finally got up there and it was my turn, I got halfway around and tipped, and I just freaked out. I couldn't move. I was just completely frozen. And there's a big long line, people waiting to get on this. And my kids were just mortified. They just, oh, Dad. So this 18-year-old that was running the event, he starts talking to me like a psychiatrist. Sir, just calm down, breathe deep, take your foot and push it forward. He talked me all the way around to the platform again. And as I jumped off the bike, he started to explain the physics to me. Okay, and I said, buddy, I understand the physics. The physics don't help you when you're out there, okay? I'm just scared spitless. So physics doesn't always help. Okay, questions on stability. Does it seem ironic that a physics professor would be talking about stability? That doesn't seem right. Okay. I have here, to introduce the idea of the heavy end, I have here two spring scales that measure force in newtons, and I've covered them up here. And what I have hanging from these spring scales is a bar, a metal bar that's 1 meter long, and it's also has a mass of 1 kilogram. And so if I put another mass of 1 kilogram exactly halfway between the two spring scales at 50 centimeters, tell your neighbor real quick what the reading is going to be on each of those scales. How many newtons will each of those scales read?
This one on the other side though.
Is that point swap to that floor? I think.
Okay. I hope that was easy for you. That's review. Okay. We still have the old rules, and that is that bar is not accelerating. It's not going anywhere. Okay. And so that means all the force down on the bar has to equal all the force up. Well, I've got a weight force on that bar of 10 newtons down. And I also have this tension force of that hanging mass that's also 10 newtons. So I've got 20 newtons down. And that means the total force up has to be 20 newtons to balance that. And there's no reason to suspect that one of those spring scales is reading higher than the other. Because of symmetry, they will both read 10 newtons. Okay? So that's old Newton. But what if I move that hanging mass so that it's 80 centimeters from the left? What if I move it, whoops, turn it around. What if I move it to there? Okay. Now tell your neighbor what the reading on the two scales will be, and then take out your clicker and vote.
Right.
So it was five. Five.
One, Mars, base two. Wait a minute. No.
Much. Yep.
They see the or some way of
Everything that's making it just wait.
The gap is.
Find that bomb.
Okay, last call.
We just finished the case.
Okay, I think that's getting to be all of us. Whoa, okay. We are all over the map. What I can tell you right now is that the answer is not A. Okay, so that means that 49 of you know that you're wrong. But the rest of you are not sure whether you're right or wrong. And that's okay, because this is a new idea. This is a pre-test, not a post-test, okay? So let's figure it out. First of all, we have to acknowledge that knowing that A equals 0 and that all the force up has to balance all the force down is not enough information. Now you notice that all of these options add up to 20. 4 plus 16, 5 plus 15, 6 plus 14, 7 plus 13, 8 plus 12. It's got to add up to 20. The old rules still apply. The question is just which of those combinations is physics, okay? Now, to answer that, we need to go back to that frictionless pond in the middle of that snowy field. And we're going to put down that meter stick again, but this time we're going to drill a hole in the bottom and drive a golden spike right through there, so that this stick is constrained to rotate about that spike as if it were a hinge, Now, if I push with 50 newtons to the left there and 50 newtons to the right there, both of those forces are 50 newtons. The forces are the same size, but they are not equally effective in causing rotation. And that's what we mean when we say torque. You know, which of those forces is going to be more effective in causing rotation? Is it F1 or F2? Shout it out. Yeah. F2, yeah. If you're trying to remove a rusty bolt from some sort of machinery, and you're pulling on that with a wrench and it's not going anywhere, get a longer wrench so that you can pull further away from the nut. And that gives you, with the same force, that gives you a bigger torque, a more effective turning force. That's what we mean by torque. See if your neighbor knows what we mean by torque. What's a torque?
I know. Like, you know, if you're like.
Okay,
I had something.
now
Multiplied by more greater.
putting the force further away from the pivot point is going to give us a bigger torque for the same force. Sometimes. But what if I push with 50 newtons there and 50 newtons there?
No.
Now, which of those is more effective in causing rotation? F1, yeah. So even though this force is acting further away from the pivot, it's not causing any rotation. If you went up to a revolving door and started pushing on the end like that, they call security, okay? They get you help. That's not going to turn the door, okay? And so it's not just the distance from the pivot, but the angle is important. It's going to be most effective when that force is perpendicular to what we call the position vector. Let me quantify it. Again, when we were dealing with linear dynamics, we always drew our free body diagrams as a dot because we did not care where those forces were applied. We just wanted to know, are they to the right, to the left, are they up or down? But when we're talking about torque and rotation, we care deeply where those forces are applied. So what we draw instead of a dot is an extended free body diagram that looks like the object, in this case, a meter stick, okay? And then we put the forces on that extended free body diagram right where they are actually applied. And then for each force, we define what's called a position vector, R, that goes from the pivot to the place where the force is applied. Now, the torque depends on the force and how far it is away from the pivot, and also on this angle. Well, which angle, Greg? It's that angle there. Now listen carefully to my words. That's not the angle between R and F. That's the angle between the direction of R, which is towards the ceiling, and the direction of F. Okay? The angle between R and F would be this one down here. But we want the direction, the angle between the direction of R and the direction of F. That makes sense? And if I do that, if I define that angle, the torque is going to be equal to the magnitude of the position vector, R, times the magnitude of the force, F, times the sine of that angle, theta. Now, you know that the sine function is biggest when theta is equal to 90 degrees. When these two are perpendicular to each other, I'm going to get the biggest bang for my buck for a given force, because that's when the sine of theta is the biggest, okay? And folks, I've got good news. 95% of the time in your homework on exams, 95% of the time, the force and the position vector are going to be perpendicular from the get-go, okay? So for example, if I had a pivot here and a force up here of 200 newtons, and my position vector was 3 meters, the angle is going to be 90 degrees there. The sine of 90 degrees is 1. And so that kind of takes care of itself. And so now the torque is just the force times the distance to the pivot. And in this case, it would be 600 meter newtons. Now I could also say it was 600 Newton meters. But when we hear that word or that combination of words, Newton meter, what does that remind you of? What's a Newton meter? Newton meter, Newton meter. A joule. That's energy, right? A Newton meter, that was Verk, energy, joules. And this is something very, very different. And so that's why I'll always call it meter newtons, except in America where we call it what? Who knows what we call it? Yes, foot pounds. And so you get a torque wrench that measured in foot pounds in this country. Okay. Now you're going to get tired of me saying this, but a torque is a force times the distance to the pivot, but they got to be perpendicular to each other. And 95% of the time they are. Well, what do I do in those other 5% of the time? Well, we've got 2 ways to go here. One way I call the useful force method. And in this method, I use all of the position vector R, but only the part of the force that's perpendicular to that R. So what I do is I break up that force into a part that's perpendicular to the R vector, the position vector, and a part that's parallel. Now, you see those 2 blue arrows? Think of those as strings that are pulling. This one pulling to the left and this one pulling up. But both of those strings are attached right here where the force is acting. So this upward force is acting right there, pulling straight up. I only put it up there because I'm going to do some trig. Okay, I wanted a right triangle, but it's really acting right there straight up. Is that going to cause any rotation? No or heck no. No. So it's only this part, the perpendicular part, that's going to cause rotation. Now, by looking at geometry, I know that this angle has to be equal to that angle by interior angles for parallel lines. And so that means that this side of the triangle, which is opposite that angle, is going to be the hypotenuse, which is F, times the sine of that angle. And sure enough, in my definition of torque, there it is right there. And so the torque is just all of the position vector times just the perpendicular or the useful part of the force. Check on your neighbor. See if your neighbor understood that.
Wow.
Actually, so. Yeah. Now it's.
Thanks.
Okay. Now, again, in this method, we used all of the R vector, the position vector, and only part of the force vector, the part that's perpendicular to R. The other approach we call the lever arm method, and it's exactly the opposite. In the lever arm method, we use all of the force, but only part of the position vector. And the way we use that method is we extend the force in both directions forever, along what we call the line of action, because the force is acting along that line. And then we find a length that starts from the pivot and goes out to the line of action such that it gets there at 90 degrees. Okay? Now, this force is perpendicular to this distance to the pivot. And remember, that's what a torque is, a force times a distance to the pivot, but they got to be perpendicular to each other. And that force is perpendicular to that distance to the pivot. Well, let's see if this works. Again, by interior angles, this is going to be also theta. And so if this is my hypotenuse, R, this is my opposite side. And so it's going to be equal to the hypotenuse, R, times the sine of that angle. Okay? And we call that the lever arm, and we use the letter L. So now the sine theta is associated with R, and I can write that as the total force times the lever arm. Now I know what you're thinking. You're thinking, thanks, Greg. Thank you so much. You gave me two different ways to calculate something I didn't want to ever calculate. Okay. But here's the thing. In some problems, the useful force method makes the problem trivial, and the lever arm method makes it messy. There are other problems where the lever arm method makes it trivial, and the useful force method makes it messy. And so it's nice to have both of these methods in your toolbox so that you can pull them out when needed. Yes, sir.
Will these give you different numbers?
No, exactly the same number. Exactly the same number. Yep. It's just in some cases, it's easier to get that number with one method than the other.
Oh, this L will be shorter than R1.
Yes. Yes. Yep. Because remember, in this right triangle, R is the hypotenuse, which is the longest part of the triangle. Okay. In both methods, I had F times R times the sine of theta. It's just that in this method, I put the sine theta with R, and in the other method, I put the sine theta with F. Okay. Thank you for asking that question. Okay. Now we're going to practice that. We're going to practice until that last exam. In summary, a torque causes angular acceleration. Now, this should feel familiar. When we were talking about linear dynamics, we found that a net force caused a mass to accelerate. It was the net force that was causing the acceleration. And so the net force and the acceleration were always in the same direction. One was causing the other. Well, in rotation, it's the net torque that causes not a linear acceleration, but an angular acceleration. Okay? And you remember the angular acceleration was the alpha that we talked about last Tuesday in the video, the alpha. Now, the direction of that net torque is given by a new right-hand rule. Well, let's remember the old right-hand rule. You remember that when something was spinning, every part of that wheel is changing direction as it goes around. Except what? Except the axis. And so what we have decided to do, and by we, I mean a group of physicists long before I was born even, they decided to say that the angular velocity vector, the omega vector, points along that axis. Now there's two ways to point along an axis. I can point this way along the axis or that way along the axis. And that turns out to be a feature, not a bug, because there's two ways to spin that thing around that axis. Okay? If I'm spinning it this way, I associate that with an omega vector that way. If I spin it this way, I associate it with an omega vector that way. And how do I remember which is which? With my right hand. Okay? What you do is you curl the fingers of your right hand in the direction it's rotating. Your right thumb will point in the direction of your omega vector. Okay? If it's going this way, I would curl my fingers like that, and now my thumb is pointing this way. Now, that might seem like the right-handed people are getting an unfair advantage. It's exactly the opposite. Because during that exam, you're going to be using two different right-hand rules. And the left-hand people are going to be able to use their right hand while they still write their answers. Okay? But you right-handed people are going to have to put down your pen to find your answer. Okay? If I were proctoring the exam, what I'd do is just look for people that were using their left hand to figure out the problem, and then I'd come over and slap them. Well, I'd have someone else slap you because I can't. I'm a professor. It's a rule, turns out. Okay. Let's talk about the right-hand rule for torque. And this is way different from the right-hand rule we just talked about. The torque is found by starting at the pivot point. And then you reach with your right hand out to where the force is applied. Now, this is the most important step. You have to turn your wrist so that you can girly wave. Yes, I said it. Girly wave in the direction of the force. And the right thumb is now pointing in the direction of your torque, which would be out of the page in this case. Now, if you can draw the R vector and the F vector on a piece of paper, the only possible directions for the torque are either out of the page or into the page. So you don't have to be really gifted with this right-hand rule. You just have to be able to tell, you know, is it out of the page or is it into the page? See if your neighbor understands the right-hand rule for torque.
Push.
Oh, we do. So is the
We did one more.
Okay.
it goes that way?
Now, just like the linear acceleration is always in the same direction as the net force, because the net force is causing the linear acceleration, the angular acceleration is always in the same direction as the net torque. How did we find the direction of the angular acceleration vector alpha? Did we use a right-hand rule? No or heck no? Heck no, heck no. We found the direction of alpha by the same method we used to find the linear acceleration A. If you're going down the freeway and you're speeding up, the velocity vector is out your front windshield and the acceleration vector is going to be in the same direction if you're speeding up. If you're slowing down, the acceleration is in the opposite direction. Well, if I spin this wheel so that the omega vector by right-hand rule is towards that periodic table, if I slow this down, my alpha vector is going to be in the opposite direction. If instead I'm speeding it up, my alpha vector is going to be in the same direction as the omega, the angular velocity. Okay? It's just the same as linear motion. When they're in the same direction, you're speeding up, opposite direction, you're slowing down. Check again on your neighbor one more time. Okay.
Mega vector is also.
So let's think about this example here. If this system, if this meter stick is free to rotate about that fixed pivot point, and if this force is always applied, say 53 degrees relative to the R vector, what's going to happen? Well, this thing's going to start rotating counterclockwise. And if I keep exerting that force, it's going to go faster and faster and faster. Well, the omega vector, by right-hand rule for omega, is going to be out of the board, out of the screen, towards you. And since it's speeding up, the alpha vector would also be towards you in the same direction as omega, right? And lo and behold, that's also the direction of the torque that's causing that alpha. That's causing that alpha. Both the torque and the alpha are out of the screen. Okay, are there questions on that? Does that seem new? It should seem old. It should seem like we've been here before, but before it was on a straight road. Okay. Let's talk about the precession that we saw at the beginning of that last lecture. If I get this thing spinning, you know, at Montana State, I used to have to do this with my hand. I used to have to just slap it until it got going. So grateful for your tithing, your parents' tithing. Buy us toys. Now, if I support this on only one end, you see that it precesses like that. Now, that red arrow represents the omega vector. By right-hand rule, it's going out that way, okay? That blue arrow represents the alpha vector. You remember we found that if the wheel's not spinning faster and faster, the alpha can't be in the same direction as omega. If it's not slowing down, it can't be in the opposite direction. Well, there's only one direction left, and that's perpendicular. And clearly the omega vector is changing because it's changing direction. It's not always the same vector. Now, I want you to take a picture right now with your phone, right? Okay, wait for it. Right now. Well, you missed it. Okay, right now. Okay, I'll help. Okay, right. I just froze time. Okay, while it was going away from you. Oops, that could have been bad. Okay, so what I wanted to do was freeze time where it was going away from you, like that. You get what I'm doing here? Okay. Now, the omega vector was out that axle, and that omega vector was changing not length, but direction. And that meant that the alpha vector had to be perpendicular to the omega vector. And so, and that's what the blue vector here represents. Now, the direction of the net torque has to be in the same direction as that alpha because it causes the alpha. Well, let's see if that's the case. I chose a time when this was going away from you right here like this, okay? And so what I'd like to do is draw an extended free body diagram for that wheel. And so that's the wheel there. And that's the rope holding it. And the omega vector was out the end of that. That's the red arrow. And the blue arrow is the alpha vector. It was away from you, was it not? Okay, is everyone seeing it? Okay, and I got to tell you, these rotational problems are inherently three-dimensional. And that's what makes them a little bit challenging. And so when you're doing your homework, I would suggest that you use props. Okay, find yourself different colored pens or pipe cleaners or something that you can hold in 3 dimensions to see things in 3D. Okay, now the first force I put on any diagram, free body diagram, is the weight force. And since most of the weight is associated with the wheel, I'm going to put it right there at the center of mass for the wheel. I then ask, are there any magnets? No. So what touches the wheel? Well, the rope, and it pulls with a tension force. Now I want to find the net torque about this pivot point that it was rotating about right here. Well, the first force that I look at is that tension force. And because it's acting right at the pivot, that's like going to a door and pushing or pulling right at the hinge. That doesn't cause rotation. That doesn't cause rotation. So that gives me 0 torque. Good, sir.
I think the motor is still on. Do you?
Oh, I can't hear it. I can't hear anything. Thank you. Was that bothering everyone else? You know, someday you'll have the benefit of not being able to hear those things at all. You know, in Bozeman, we had a big old train track next to our house. Didn't bother me a bit. Trains went all night long. Okay. Well, let's look at the torque caused by this weight force. Again, right-hand rule has me start at the pivot. I reach out to where the force is applied. I turn my wrist so that I can wave in the direction of the force, which is down. My thumb is pointing into the screen, and that's the direction of the torque. Now, the net torque is the torque due to this force plus the torque due to that force. But this torque is 0. Does everyone see why this one's 0? It's acting at the pivot, so there's no lever arm. No lever arm. So this torque is causing that alpha. Okay? Now, if I had spun that thing the other way so that the omega vector was going the other way, it would precess the other direction. Net torque is always in the same direction of alpha because it causes alpha. We call this the wheel of serious injury because at Montana State, our provost, Jack Drumheller, a physicist, was teaching the class, and he had a very heavy wheel that was weighted with lead, and it had spokes. And when he tried to put it into the cradle, it jumped and took off across the table, and he grabbed it, and there were stitches involved. It was messy, blood. Okay. It turns out that if the net torque is 0, the alpha is 0. There's no change in the omega. Omega is constant. And we've been there before. When the net force was 0, we called that equilibrium. and we had zero acceleration. We're going to find on Thursday that if we double the net torque, we also double alpha. So just like in Newton's second law, they're proportional to each other. And when you double one, you double the other. Now, this idea of torque explains that concept of stability. Why does the center of mass want to be right underneath the support? Well, that's because the weight force always acts at that center of mass. And if that center of mass is directly below the support, when I extend the line of action, it goes through the pivot point. There's no lever arm. There's no rotation. But if I move that center of mass off to the side, now when I extend the force in the line of action, it doesn't go through the pivot. And so I have a lever arm. And so the torque is going to be this weight force times this lever arm, and it's going to make it rotate back to where it gets to this position right here. That's the explanation of what we saw with the shovel and the pitchfork. Okay? Now, let's put it all together. Let's put it in a way that you can solve problems with it. If I had a very, very strong but light pole made of graphite epoxy or something that was 1 meter long, and it was free to pivot without friction about that point right there. There's a spike right there holding it in place. Okay? If I hung 200 newtons from this end, that would just fall to the ground. That would pull the bar down and just make it rotate. If I didn't want it to rotate, I would have to pull right there with 200 newtons to support this 200 newtons. But here's where it gets weird. If I move that spring scale there, halfway down the pole, now I have to pull with 400 newtons. Well, how did I get that? How did I get that? Well, the same way I used to argue with linear dynamics. If you had a block that was not going anywhere, and I had two forces to the right, one that was 100 newtons and one that was 150 newtons, and only one force to the left, you could figure out easily what that force to the left was. It's got to be 250, because what you're using there is that all the force to the left balances all the force to the right. Well, in this case, that thing is not angularly, rotationally accelerating. In other words, alpha is 0. And that means all of my torque has to add up to 0. Well, I like to think of that torque as clockwise torque and counterclockwise torque. This heavy weight here is trying to make that bar rotate clockwise about that pivot point, about that hinge. This pull by the spring scale is trying to make it go counterclockwise about that pivot point, about that hinge. And those two have to balance each other, okay? Now remember, torque is force times a distance. So that means 200 newtons times the distance to the pivot of 1 meter, that's 200 meter newtons. That has to equal this distance, 1/4 of a meter, times this pole. And that makes that pole 800 newtons. Because 800 times 1/4 gives me 200. And that's what I had here. See if your neighbor understood that principle, because that's vital. That's the crux of it. Okay. We have 5 minutes. And in those 5 minutes, I want to solve this problem that we started with. First of all, acknowledging that nearly all of you got this wrong. And that was okay, because we were starting out.
I put the wrong answer.
But now let's get it right, okay? Remember, the old rules still apply. that bar does not have a linear acceleration. So that means that all the force up has to balance all the force down still. That means the force by the left spring scale plus the force by the right spring scale has to add up to 20 newtons. But that wasn't enough. So now we're going to use the fact that that bar is also not angularly accelerating. Its alpha is 0. And that means all the torque has to be balanced. All the clockwise torque has to balance all the counterclockwise torque. Now remember, we're looking for two tension forces. One tension force exerted by this spring scale on the bar, and the other one exerted by this spring scale on the bar. These are forces on the bar. So I want to draw an extended free body diagram of the bar. Now, the first force I put on any diagram is the weight force. And folks, this you can take to the bank. You always, every stinking time, put that weight force at the center of mass. I'm going to tempt you on Thursday to put it somewhere else. Don't give in to temptation. It always goes at the center of mass, regardless of what's going on around it. Okay? Now, there's no magnet, so what touches the bar? I've got that tension force of 10 newtons down there, and I have the two spring scales pulling up. Now, before I can balance the clockwise torque and the counterclockwise torque, I have to ask myself, what's the pivot point? Well, it turns out this bar's not rotating about any point. So I'm free to choose any point as my pivot. I can choose that point, I can choose that point, I can choose that point. I can choose a point in Kansas. And whatever point I choose, the torque clockwise is going to balance the torque counterclockwise. But I'm here to tell you that if you don't like solving two equations and two unknowns and doing some fancy math, there's only two smart places to choose your pivot. And that's because if I choose my pivot to be here, I eliminate the torque due to TL. If I choose my pivot to be here, I eliminate the torque due to TR. I can't solve one equation with two unknowns, and so I want to get rid of one of these unknowns. So I do the smart thing, and I choose my pivot to be right here. And now I try to figure out which of these forces is giving me a clockwise torque and which is giving me a counterclockwise torque. I pretend that there's a big old spike or a hinge right here, forcing this bar to rotate like a door around that point. And then I ask myself, what would this force do to that door that's forced to pivot about that hinge? Well, this force is trying to make it go clockwise. This one's trying to make it go clockwise. This one's trying to make it go counterclockwise. And this one's doing nothing because it's acting right at the pivot. This gives me nothing. So I set up my equation thus. These are the clockwise torques. I've got 10 newtons here times its distance to the pivot of 0.5. I have this 10 newtons here times its distance to the pivot of 0.8. The counterclockwise torque is this unknown force times its distance to the pivot of 1 meter. When I solve that for my unknown, I get 13 newtons. It's all got to add up to 20. So this is 7 newtons. Now, if we go back, what we find is that 26 of you got that right, okay? But now you understand what the right answer is. Are there questions on that? We're out of time. We're going to practice and practice and practice this on Thursday. Be sure to come on Thursday. I think you'll find there's going to be a treat.
Fine.
Okay.
For last day. It's my own.
We made it.
Yeah.